solutions, or one version of solutions for perfect problem 7 for 243. Basically, the idea here is I want you to do 2 hypothesis tests, one that's a t-test and one that's a proportion test. So kind of the next 2 topics that we're going over. So we'll kind of do these one at a time. Maybe I can squeeze them both into the same thing. Over here in the t-test, basically, what do we got? I claim that in NBA playoff games, more fouls are called. To test this hypothesis, I use a sample of 64 NBA playoff games. It tells us that n equals 64. Thus far in this season, I found that on average 41.95 fouls are called. This is in my sample, so 41.95 is my x bar. With the standard deviation of 5.8. The standard deviation is of my sample, so this tells me that S equals 5.8. In all NBA games this season, there have been an average of 40. So talking about all, kind of a population keyword there, tells us that mu naught is equal to 40. And lastly, we want 99% confidence here. So that tells us that alpha is equal to 0.01. So now that we pulled all that information out, we can go ahead and start solving this thing. First step in hypothesis testing is to state your null hypothesis and to state your alternative hypothesis. Denote those as H0 and H1. The alternative hypothesis is the claim. I claim that more is kind of the key word here, fouls are called. So my alternative hypothesis is that mu is greater than this population parameter of 40 right here. Mu is greater than 40. And my null hypothesis is that mu is equal to 40. What I have here is a one-tailed test. It's actually a right-tailed test, which you can write if you want. Okay, and kind of the next step is to calculate your test statistic. We're going to use the letter T for this test statistic. The reason why is this is a t-test because we know S instead of sigma here. Our test statistic is x bar minus mu naught divided by S over root n. That's supposed to be a minus sign in there. And we have all that information up here. X bar was this 41.95. 41.95. So 41.95 minus mu naught was 40 divided by S was 5.8 divided by the square root of n, square root of 64. So if you plug all that into a calculator, that is 2.69 if we round to 2 decimal places for our test statistic. Okay, moving on to the next step, we're going to draw our sampling distribution. I'm going to draw it approximately normal, although that's a pretty bad picture. Let's try again. A little better. Draw it approximately normal. Why can you draw it approximately normal? Maybe note this is approximately normal because n is greater than or equal to 30. And in this case is, 64, which is definitely bigger than 30. So our central limit theorem tells us that this will be approximately normal. Okay, so we have a right-tailed test. That means my rejection region is going to be over here on the right-hand side. And alpha is 0.01. So the area of my rejection region is always alpha. So that means this area is 0.01. So what I have to do is find the critical value off my t-tables. Let's see, we have, I guess I wrote it up top. N was 64, so that tells us we have 63 degrees of freedom. So if you go to your t-tables and you look up the column that has 0.01 for the area in the right tail, and then 63 degrees of freedom, that one doesn't show up. There's a 60 and a 70. They'll be pretty close. I'll use the 60 just because it's a little bit closer. That gives me 2.390. So my critical value right here is 2.390. Okay, my test statistic here, this 2.69 is greater than this 2.390. In other words, it's in the rejection region. So I can therefore conclude, maybe I'll say something like, because my test statistic is in the rejection region, there is sufficient evidence to reject the null hypothesis and conclude, let's see, what were we talking about in this problem? More fouls are called in playoff games. And conclude more fouls are called in playoff games. Something like that. And that ends the first half of this problem. There's another half, which I'll tackle over on this side. It's a proportion test. So you go through here, you kind of read through the problem and try to find all the pertinent information. Really, there's only a couple things we need. First of all, that n is 64. See here, I'm claiming that the importance of home court advantage is different. That's a key word right there in the NBA playoffs. To test my claim, I looked at 64, that's my sample, playoff games so far, and I found that the home team won 65% of its games. That tells us that p hat is equal to 0.65. In all NBA games this season, the home team has won 58.67% of the time. So that tells us that P naught is 58, maybe 0.5867. And I want to test my claim with 95% confidence. It tells me that alpha is 0.05. Do these same steps. The first thing I want to do is state my null and alternative hypotheses. So I got the null hypothesis and my alternative hypothesis. My alternative hypothesis comes from my claim. I claim that the importance of home court advantage is different. That is, I claim that mu is not equal to P0, 0.5867. And my null hypothesis is that mu is in fact equal to 0.5867. Because this is not equal to, this will be a two-tailed test. Now I want to calculate my test statistic. It's a z statistic in this case. Proportions are always z because we're only estimating one parameter. Our formula is p hat, what we got out of our sample, minus p naught, what we expected, divided by our standard deviation, which is p naught times 1 minus p naught divided by n. Be careful, make sure you use p naught here, not p hat. Kind of the idea is we're assuming our null hypothesis is correct. Shoot. There you go, I fixed this. It's supposed to be p, not mu in here because we're talking about proportions. So I fixed my null and alternative hypothesis. Anyway, down here we're assuming that our null hypothesis is correct. So we're assuming that p equals 0.5867. So really, since ideally we'd use p in this formula and we're assuming that p is equal to p naught, you write p naught down here. So let's see, p was 0.65, p hat was 0.65, p naught was 0.5867. And we're going to divide that by the square root of p naught, 0.5867, times 1 minus p naught, which is 0.4133, and that whole thing divided by n, which is 64. And you plug that mess into a calculator, you get 1.03. It's supposed to be a 1. 0.03. As our test statistic. Alright, so now we're going to go ahead and draw the picture. Here's my sampling distribution. Maybe note this is approximately normal because n times p hat times 1 minus p hat is greater than or equal to 10. It should be p naught times 1 minus p naught, not p hat in this formula here. I don't think it'll matter either way. We'll satisfy this criteria because 64 is plenty big. 64 times 0.5867 times 0.4133 is greater than or equal to 10. Guess I should figure out what that number actually is. Add all these together, what you get is 15.52. Exact value isn't that important, just the fact that it's greater than or equal to 10. So this thing's approximately normal for that reason. So we can draw this shape. I tried to make it normal here. It's a two-tailed test, so we're going to have two rejection regions, one on this side, one on this side. And the total area of my rejection region is alpha. So that means the area over here is 0.025, and the area over here is 0.025, because they have to add up to give me 5%. So then what I need to do is figure out what critical value has 2.5% in the upper tail. You can figure this out using your calculator or tables, or you might remember from the confidence interval chapter that that's 1.96 and negative 1.96 that correspond with that level of confidence. So then what we do is we look at our test statistic here, this 1.03, and the test statistic does not fall in the rejection region, right? It's less than 1.96. Maybe it's somewhere over here, 1.03. So because of that, because my test statistic is not in the rejection region, there is not sufficient evidence to reject the null hypothesis. So we are not saying that the null hypothesis is correct. We're not saying that there's no difference between home court advantage in the playoffs and in any other game. We're just saying there's not sufficient evidence to conclude that there is a difference in those things. And I think that's good enough. There's some couple of examples of hypothesis testing. That's the end of the video.